Yeah, the next topic is titration of a weak acid with strong base. Okay, in order to titrate weak acid or weak base, we need strong base or strong acid because weak plus strong makes the reaction to complete. Okay, but weak acid with it is possible to titrate the weak acid with weak base or weak base with weak acid. Yeah, it's possible, certainly possible, but we are not sure whether the reaction goes to completion or not. If the reaction doesn't go to completion, and then our pH calculation may be wrong. All right, so that's why it is a usual practice to use the strong acid or strong base as titrant. Okay. So here titration calculations for this problem are of four types. Okay, first is a before any base added. Okay, the solution contains just weak acid in water. Okay, right. This is the initial pH. Yeah, before the uh, strong base is added. Okay, so reaction is this one: simple dissociation of weak acid. Okay, Ha dissociates into protons and anions. Okay, and second is that the addition of strong base, sodium hydroxide, before the equivalence point. There is a mixture of unreacted weak acid form and anion form. Aha, since we have these two components, that is a buffer. Okay, and then we use Henderson-Hasselbalch equation to find the pH. Okay, this equation can be very um, usefully employed. All right, and third, third region is at the equivalence point, or weak acid has been converted into anion. Okay, by adding strong base. The same solution could have been made by dissolving, you see, sodium, this one, anion, okay, in water. Since at the equivalence point, this HA form disappears, okay, only we have this anion form. So that situation is equivalent to the situation when you add sodium anion in water, okay, so pH is determined by weak base, this anion, okay, this anion is a weak base in the equation is like that. This anion reacts with water to give weak what acid and hydroxide ion, you see. So since it makes this hydroxide ion, so the um, pH must be beyond 7. Okay, and in the fourth region is the beyond the equivalence point. At this point, excess NaOH is added. Okay, so in solution we have this anion and also the hydroxide ion. Okay, two basic solution, basic species. But hydroxide ion, which is much more strong, yes, it's a stronger base than this anion A minus. Okay, so pH is determined by strong base. We neglect the tiny effect by association of this anion with water. Okay, so we divide the titration curve into four parts. Okay, initial pH and what before equivalence point, at the equivalence point, and beyond equivalence point. Okay, okay, let's take an example. Titration of 50 milliliters of 0.02 molar MES. Okay, MES is this one. This is a weak acid with zero point 0.1 molar sodium hydroxide. Yeah? This MES is 2 and morpholino ethane sulfonic acid. Yep, this is a weak um, uh, this is weak let me say base, okay, anionic form. Okay, this is MES here, this one. The proton here will be dissociated. Okay, so this is a weak acid, and we write in short HA, right? pKa is 6.27. Okay, so this is weak. Yeah, let's consider the pH change as we add this strong base. Okay, um, first what we have to do is to calculate the equivalence point. Okay, in other words, how many milliliters should be added to the solution to reach the equivalence point. All right, and okay, let's start. And when the strong base is added to this weak acid, then reaction is like that. It goes to the equilibrium. It's far shifted to the right side. Okay, for example, we can calculate this equilibrium constant. Here, the equilibrium constant K equals what? The inverse of Kb. Okay, since this Kb is what? Kb is Kw divided by Ka. Since Ka is 10 to minus 6.27. Okay, so we can easily calculate the equilibrium constant for this reaction, which is 5.4 times 10 to 7. Okay, wow, this is a very big number. So we can simply say this reaction goes to completion. Okay, we don't have to consider this reverse reaction. All right, and let's calculate the equivalence point, which is the volume to reach equivalence point. Okay, and uh, the initial volume of this weak acid is 50 ml, and the concentration is 0.02, and a strong base concentration is only 0.1, and then we need volume for equivalence point. And we solve this equation, and then we get Vb equals 10, okay, ml exactly. Yeah, that's the equivalence point. Okay, now start to calculate the pH for four regions. Okay, the first region is the initial pH. Okay, before base is added. Okay? We simply we write this dissociation, and then this dissociates by x. Okay, and then we set up this equilibrium equation, and then we solve for x. Here x is the proton concentration. Yeah, now is 1.03 times 10 to minus 4. So pH is, this is initial pH, right? Is 3.99. Okay? That's the initial pH, yeah? Region 1. And then we move to the before the equivalence point. Okay, let's assume we added sodium hydroxide. How much volume? We have to let me see. Here, okay, let's assume we added 3 ml of hydroxide. Okay, 3 ml. Now, volume increases from 10, right? Initial volume was 50 ml, and then now we added 3 ml of sodium hydroxide, so volume increases to 53. Actually, that doesn't matter. All right. Okay, titration reaction is this one. HA, reacts with hydroxide, okay, to give anion and water. Okay. Since initial quantity of HA, let's say, is 1, let me see. And then just a second. You know, it is not very clear. Okay, let's temporarily stop now. Okay, yeah, right. Yeah, the 3 ml of hydroxide was added. Okay, since the number of moles of added hydroxide ion is what? 0.1 times 3 ml times 0.1 is what? 0.3 mole. Okay, but initial mole of MES is what? 1 millimole. Okay, so when 3 ml of hydroxide ion is added, actually it reacts with this one, but still in solution HA, no, weak acid form still remains. Okay, this is the initial condition, right? Initial mole of HA is 1 millimole, and hydroxide ion of 0.3 millimole was added, and then it reacts. So remaining mole of HA is 0.7. Okay, and produced mole of anion is 0.3. Okay, and we apply Henderson-Hasselbalch equation here. Okay, pH equals pKa plus log, okay, anion concentration divided by this one, HA form. Yeah, this concentration. Since the volume is the same, so instead of considering the total volume, which is 53, okay, milliliters, since we simply consider the moles of produced anion and remaining HA, okay, which is 0.3 divided by 0.7, and then pH is 5.90. Okay, when 3 ml of hydroxide ion was added. Okay, and the special point is that um, when you added just one half of equivalence point volume, okay, when V equals one half of VE, okay, in the case the concentration of anion and HA are the same, okay, so it cancels out. Log 1 is 0, so pH simply becomes pKa. Okay, here's the illustration. Okay, when 5 ml of hydroxide ion was added, okay, so HA, mole of HA and mole of A minus are the same. Okay, so pH is pKa. You see, very simple. So this is a very good way to experimentally obtain the pKa of weak acid. Yeah? So when you have a very nice titration curve, okay, and then you find equivalence point, and then the halfway, exactly halfway, the pH is pKa. All right. Yeah. So this one, since in this case the solution contains these both species, yeah? This is a buffer, okay, working at pH of 5.90. Okay, the next region is at the equivalence point. There is exactly enough NaOH to consume HA. Okay, now when um, the number of moles of hydroxide ion is exactly the same as HA, right? That's the equivalence point. Only an ion, this species remains in solution. Okay, yeah. This concentration of HA and hydroxide ion is almost negligible. Okay, yeah. Since an ion is in the solution and it undergoes a reaction with water to give HA and hydroxide ion. Okay, then equilibrium constant for this one is Kb, and Kb equals Kw divided by Ka. Since we know already the Ka for MES, right? We can calculate Kb, and then let's put the concentration of HA and hydroxide ion as X, and then we can write this equation. All right. Here is the one only trick point. The formal concentration of A minus is no longer 0.02 molar. Right? Why? Because the hydroxide ion was added. Okay, yeah. Diluted. Yeah. So here, first we have to calculate the formal concentration of hydroxide ion. Okay, by this equation. Number of moles of hydroxide ion. What is that? It is the same as added moles of hydroxide or initial moles of HA. That's the number of moles of an ion at the equivalence point. Okay, here's the so what was the initial mole of HA? That is so here we we see the question 50 ml times 0.02 molar. So if you multiply these two values and we get 1 millimole. Okay, 1 millimole is the initial mole of HA, and we divide by the volume. Okay, since 10 ml was added, okay, of hydroxide ion, so total volume now becomes 60. 50 plus 10. All right, so 1 divided by 60, okay, gives you this number, 0.0167 molar, right? That's the anion concentration at the equivalence point. Okay, here so F is 0.0167. Okay, and we solve this equation. Then we get X value, yeah, which is 1.76 times 10 to minus 5 molar. Okay, this is hydroxide ion concentration. So we can calculate pH, yeah, and so minus log Kw divided by this hydroxide ion concentration, and then pH is 9.25. All right, which is the pH at the equivalence point. So now we know that when we titrate weak acid with strong base, and then the pH at the equivalence point is over 7. Okay, all right. Likewise, we can say that when we calculate titrate this weak base with strong acid, the pH at the equivalence point is below 7. Okay, yeah. Okay, now let's consider the region 4 after equivalence point. Okay, let's assume you added just 0.1 millimolar more than the equivalence volume. Okay, now let's see how pH increased. Okay, when you added 10.1 ml of sodium hydroxide ion, so there is excess mole of hydroxide ion. Okay, how much? The mole of OH minus is that 0.1 millimolar milliliter times the initial concentration of hydroxide ion, okay, which is what, 0.1, and then you have to divide by total volume, which is 50 plus 10.1, okay, here, and then you get this number 1.66 times 10 to minus 4 molar. Okay, so the proton concentration is Kw divided by this number. Okay, here it is, and then pH becomes 10.22. Okay, you see, um, the at the equivalence point, the pH is 9.25, but when you added just 0.1 millimolar excess of hydroxide, solution, and then pH increased to 10.22. Yeah? The pH increase is about 1. Okay, a lot. Okay. Okay, yeah, this is the titration curve. Okay. Now you start. The initial pH is around here, and then as you add strong base, okay, and pH increases, yep, increases, and at the equivalence point, yep, the pH increases a lot by simple small addition of strong base. And after equivalence point, pH increases but slowly. All right, yeah. So in this region, yeah, between what this equivalence point VE and this one initial the zero, this area is the what, since HA and A minus, two species are present in solution. That is the buffer region. Okay, but maximum buffer capacity is obtained at exactly the halfway, the middle point, hmm, before the equivalence point here. That's the buffer of maximum capacity. All right. So this table shows how pH changes as you add strong base. Okay. So this is not very difficult to understand.